Yeah, so the recording has started. Everything is still recorded. Nothing is lost. So first, the neural network workflow. So for a recap, I will be going through the pipeline, the neural network, the training pipeline. There are two big important points that we raised last time, which are the forward pass and the backward propagation. We also shared about how the neural network works under the hood, as well as we also shared about the activation function, right? So on the screen, I put one piece of activation function, which is the ReLU activation function. ReLU stands for rectified linear unit. Rectified in a sense that it is if you are electrical engineer, you might have like noticed this curve looking like a diode, right? The diode. So it only allows the current to flow one way. So the idea is that any value below that is negative, it will be 0, and any value that is above, that is positive, it will be linearly proportional into 1. So why might this be the case? So this activation function is used to uh, to increase the gradient propagation. If you recall last time, one of the important activation function that we shared is the sigmoid function. So the sigmoid function is very smooth in a sense that there is no discontinuation, or there is no sharp change in gradient. And as you approach infinity on the x-axis, either way, the gradient decreases to 0. So when the gradient decreases to 0, it is very, I would say, bad, because we use the neural network use the gradient in order to update its weight. So if the gradient is small, we are not updating anything. So with this value, we divide it into like two regions. One is the non-activation region, which is negative. If it is negative, then it will become 0. And if it is positive, then we will have the linear relationship, so that the gradient is locked. So as you can see, the gradient now is like 1, right? Yes, the gradient now is 1. And for the on the other side, why do we want it to be like 0 and 0 gradient? It is to prevent various numerical explosion. So for example, if the value is 0.001, you might think that it is very insignificant, but the forward pass and backward pass will also cause some numerical instability. So therefore, after many trials and errors, researchers found that, okay, this ReLU function is quite nice. So that's why you might encounter this in many of the new models that are being used today. And I think later on, you will also encounter that as well. So now let's get back to the training loop. So first we have the big box at the top. So first we have to define what is our model, and we have to define what is the forward pass, how it is, how does the signal propagate to our model. Then there are two aspects when we use this model. One is for training, one is for inference. Inference is when after the training, we use the model on its own and put the input through and just use the prediction right away for your real life task. The interesting part happens in the training. So in the training, we will be looping over the data set. So what are the steps of along the way? So first we have to take the data, put it through the forward pass of the model to get a prediction. From this prediction, we will then calculate the loss function, the cost function, which is the ground truth, right? The label, the ground truth. So along the way, you can you notice that I use a lot of synonym, because that is what happening in the research community. They keep using the different words to point at at the same thing. But as long as you know what is the core idea, you will be good. So the loss, the cost function. So after you get the loss, then we will then be calculating the gradient with respect to what? The gradient of the loss function with respect to the different weights, all of the weights in the model. Then we will be updating the weights, and we will print out the loss value, the epochs, the time taken. so that we can have keep track of the record of what we have been doing. Then we test the training, we test the model and save out the state of the model for future use, for inference. Yes. So one of the loss function that we might have moved past quite quickly was this idea of cross entropy. So you might have heard of the term mean square error. You have learned that from your linear regression, from many of your like line fitting algorithms. So mean square error is quite easy to use. You have a goal, a target, then you measure where you are, like how far you are from the target, and that will be the cost that you want to minimize in order to reach the target. But what about classification? In classification, like maybe you might not know, okay, so in classification, how do we quantify how close we are to the desired classification? So last time we introduced this idea of the binary cross entropy function, and it is formulated as yi log probability of I. There's a lot of things that is happening there, and then there's also like 1 over n. So the idea of 1 over n is just aggregating the average of various data set of various data points. So it will appear from time to time, but you just think of it as you just average out. You don't take each data point and operate on it directly. You average the cost of various data points. So how do we visualize this cost function? The idea is that if the label is number 1, is 1, y equals 1, then we will be punished. The cost is high if we predict 0. So, and similarly, if the label is 0, if the label is 0, then if we predict 1, the cost will be very high. So that is like the simple heuristics of how you can use this function. Then the next question might be, okay, that is one case of 2 classes, 0 and 1. Cool. But what about multiple classes? How do we deal with that? So in this slide, I will be introduced you to the idea of a softmax and the cross entropy loss. So the cross entropy loss is a more generalized version of the binary cross entropy. Or in fact, you can say binary is the special case of cross entropy. So the idea is that if you recall your neural net, at the end of the neural net, you can have multiple nodes. So individual like node carries a value, right? So what might that value mean in our context? It can mean the probability of a dog given the input. So xi in this case is the input. So given this image of a dog, what is the probability of it being a dog? So that is one way we can interpret the end node, the final layer of the neural network. So in here, you can see that the neural network is a black box. We don't care. We just know that at the end, there are, let's say, 10 classes. So each classes will be, each classes is we denote a probability. But as you know from the training, like the numbers can be anything. It can go from very large to negative number. So this cannot be interpreted as probability, because probability cannot be greater than 1. The sum doesn't add up to 1 and it is negative. So how do we rectify this? So we rectify this using a softmax function. It is called softmax. The idea is that we will take the exponential of each of these values and divide it by the sum of those exponential, so that we will resolve them as in this case, right? So it is not similar to the scaling, but it has that idea of a scaling factor into distribution, into probability. So if the value is 4.4 and 4.4 is definitely higher than the rest, then in terms of probability, it is like 0.8. So it's very high. You can see that negative 0.4 is even lower than 0.1. So the probability is like close to 0. So 0 and 0.1. Yeah. So it converts all those numerical values that is out of bound of probability neatly into a probability that can sum up to 1. So this is the idea of a softmax function. Yeah. So okay. So how then do we interpret this step? So next, the way we interpret this is to, let's say, plot a bar graph to denote the distribution. So instead of stacking them up in vertically like this, we'll be stacking horizontally. So on the x-axis are your classes, and the vertical axis, the y-axis, is the probability. So in this form, you might have realized that, okay, this is more familiar. It is just a distribution. In this case, it is a discrete distribution. So we have our predicted distribution will be the green one. Like there are various values because, because there are different nodes, and different nodes give different values. But in the label is very clear cut. One spike at the dot, and everything else is 0. So then the idea is that we want to compare, like how close or how far these two distributions are, how close and how far the red from the green distribution. So then this is, we will be using what is called a KL diversion at the bottom. So we will not be going through what KL diversion is, but you can see that it has the similar form. The label times the log of the probability, similar to the binary classification, binary cross entropy. So yes, in simple terms, in order to interpret what is cross entropy loss in classification, you think of the n layer as a list of probability distribution, and the labels will present a different probability, and you ask how close are these probability to each other using this function. Yeah, that is the visual explanation. I will not go down to the math, but let's move on. Yeah, so this is, I just want to clarify this particular loss function in the case of classification. Yeah. So now we'll be introducing to the idea of data cleaning. Previously, we have introduced the idea of cleaning in the context of tabular data. So you have your empty spaces, and we want them all to be filled. Therefore, we need to filter out the bad one, right? So that is the process that we want to achieve. And the clean data is very clear cut. Any missing value, outliers, inconsistency will be thrown out. Yeah, handling missing data, deletion. This thing I think we have been through. Removing outliers. These can be like easily visualized because they are scalar number. We can plot them on a graph, but it is harder in various cases, such as, let's say you have natural language or images, then how would you interpret this thing? So probably you don't, right? Probably you cannot filter them all very nicely, but you can improve the robustness of your model using data augmentation. The idea is that you have, originally you have a dog, but then when you crop or zoom in on this image, it should still give you a prediction of a dog. Therefore, we can use various tools and techniques such as cropping, resizing, distortion of color, so to make our model more robust. Because even if we change the color space, right, the contour and then the highlighting, the shadows of the dog should show us the dog. And if we want the models to be very good at a lot of things, then probably we want them to handle various cases as well. So this is another stage in the pipeline where we do not necessarily collect more data or discard or remove. We just use what we have and augmented it in various ways to get more data, more information out of it, right? So you can also have rotation, flipping, cropping, adding noise. Yes, so in terms of audio and text, we can like add noise or synonym replacement, and there are various libraries that you can use. And again, we are introducing you to this new idea, but we won't be going through them all. If you encountered any, so when you are doing your real problem, then you might recall what might improve your performance. Then you will reach out to all these libraries. And in this slide, we will be sharing the slide as well. We have embedded various links down below for you to follow if you are interested. Okay, so now another idea of data manipulation is the idea of normalization. Previously, I think one of the Q&A, one person in our session asked this idea, like, what about normalization? Because the value that you put into the neural network can explode, right? It can span, the range of the values can be very large, and different features might have different range. So that will complicate the weight updates. So yeah, the idea is when we want to normalize, we want to make the model converge faster and make all features relatively equal, of equal importance. And this is, yeah, it is very useful in the case where the features are like all over the place. So in the visualization, you can see that the unnormalized data is like an ellipse. So the idea is that when you gradient descend, when you step down the hill, when you update the weight, it will bounce back and forth along the direction that give it a lot of downhill. But then that downhill is big purely because of the range of the data. It might not be the best way to go, but because the numerical value is so large. Yeah, therefore, it can introduce various wrong direction, like wrong exploration direction when we go down the hill. Yeah. So when we normalize, everything is like relatively circular and relatively normal. All features have equal weight. Then we can converge even faster. So normalization techniques, various normalization, we can min-max and then scale them accordingly, or we can use this Z-score. If you have learned probability and statistics in your respective school, EEE or CS, then you might have heard of this Z-score when you try to do the normal distribution. Yep. And there's also this idea of batch normalization as well. So in batch normalization, yeah, you normalize all over the, you using all of the features. Okay, so now data. Last time we did share with you, we did introduce the idea of train and test, because we want to train the model, train the weight, and then we want to measure how good the model is at the end of the training. So train and test. But now we want to introduce the idea of a validation data set as well. So the validation data set is used to fine tune the model, as well as it also gives an estimate of how good the training or like how good the weight updates are as well, as we will be elaborating in the further. So yes, so the idea is we want to prevent overfitting, and we will elaborate later. At the moment I will be sharing, okay, where does this validation data, how does it fit in our current workflow? So our training data is what is used to update the weight, right? Then the validation model happens after we update the weight. So when you update the weight, the model has a certain state, right? Then we test that state of the model to see if it works well or not. And then when we look back, when we update the second time, the state has changed. And we want to ask, okay, is that state better than the previous one? So what does that mean? So during the training, because we keep on training on top of the data of the training data set, definitely the error will be slowly decreasing, because that is the thing that we ask our model to do. We have a cost function, we have a cost, yeah, and again, another synonym, error, cost, loss, same thing, the same thing. So we want to minimize the error, we want to minimize the cost. Definitely it will reduce as we train more and more and more. But at some point, our validation, so this validation is like an intermediate test. So we don't use the validation data to train. So it has not seen this info at all. The weight is not updated based on the validation. But using this validation, we can see that, okay, at some point, it starts degrading in its performance. So this is where we can know where to stop early. Yes. And then, yeah, the idea is the same idea of data splitting. We can do it randomly. We can do it based on the class distribution. because the idea of maintaining class distribution is, for example, we have a lot of dogs and cats around because we breed them so much. But sometimes, like let's say we don't have a lot of information of the platypus. So if we choose randomly splitting, we might have more dogs and cats than platypus. So when we stratify split, we say, okay, each classes we will take 10%. So the platypuses will be in the validation test accordingly, right? So then time-based split is for time series data. Like, do we chop them? Do we take the test at the very end so that it can predict the future? Or do we want it to get the historical data for them to learn it as well? So those are the various data splitting techniques, where to split and how to split them. Okay, so this slide is just to introduce you to a very interesting aspect of like data. Previously, in the last workshop, we use the data that is in the library. So we call the library download the data from the cloud, and it was relatively lightweight, probably less than 1 gigabyte. But in bigger data set, they do not just have an image and a label, but they do also have annotation, a lot of annotation for various aspects. So here is like a COCO data set. It's called Common Object in Context. And the images is in a JPEG file, and the annotation is in a JSON file. JSON file is just a file format that can compress a lot of, not compress, that can hold various form of data. And when you read it using Python, it will come out as a dictionary. So dictionary, in CS term, it is like your key, your hash table. You have a key and then you have a value, key and value pair, similar as that. So you can see over here, yes, there is a train, validation, and test images. So they also have already split out the various images for us to various data folder for us. And you can see on the right, yes, the JSON file embedded various label. Previously, what we did was like, okay, there is a image of number 0, and we label that whole image as 0. So it's very easy, one simple label. But here you can see that the person is on the street riding a motorbike. So what are the labels? So one box is for the motorbike, one box is for the person, one box is for the elephant at the back, or something like that. So there are various things happening in the same image with different labels for different tasks. So the bounding box is probably for detection. The blue mask that you are seeing is like it is called segmentation. So segmentation happens when, let's say, your iPhone and your portrait mode, right? When you use your iPhone and turn on portrait mode, yes, probably it detects your face, but it doesn't detect it as a box. And if the phone wants to blur out the background, it doesn't blur out the boundary of the box, because some background can still be inside the box, the bounding box. Therefore, segmentation nicely crop out your face in a weird shape, oval shape. So those are the various tasks in the machine learning and deep learning pipeline that you can use, and they have the annotation separately. So the point of this sharing is just that in the future, if you engage with machine learning, the data reading and data processing part is very crucial. At the moment, we're just sharing the baby step. So you might think that it might be easy, but in the future, a lot of things are very difficult and time consuming. So, okay, hyperparameters. I have been sharing about batches and epochs a lot, but what do they mean? So epochs, it is like, it's the number of time you have looked through the data. So in the data set, you have, let's say, 1 million data points. So in a data set, you have 1 million data points. And every time the model see all of the images, or like all of the data, 1 million of them, we count that as one epoch. So why do we count this way? Because we want to go through the data set a lot of time. So a batch is like, a bunch of something, right? A batch. So it's the number of the data that we will be using to update the weight. It is the number, it is the letter N that you have seen just now. So the idea is when we update the weight, we can, like, technically we can go one data point, read through, forward, backward propagation, update the weight, second data point, do that again. We can do that, but it will be very time consuming. If we have 1 million data points, that will be a million updates, and that is not very efficient. Therefore, what we want is we want to divide them into like batches. So, okay, wait. On one end, we can go individual data point. On the other end, like on one farther end, is like we look through 1 million data points, put n equals 1 million, and average them all. So that will be even more time consuming. So what is the middle ground? The middle ground is having like this. You can call it batch or mini batch. So instead of taking the whole data set or one of it, we take some of it, so a batch. So therefore, there's also this idea of an iteration per epoch, which is all the data divided by the batch. So yes, we want to divide the whole data set into small various batches, and let's say 4 at a time. And when we do 4 at a time, it should be like random, right? Because we don't want to make in order, because if it's ordered, then you also introduce a certain like temporal time biases, like, oh, you keep reading in this sequence, and I will keep updating in the same sequence because I keep seeing I keep seeing the dog before the car. So I will update my weights to favor the dog, something like that. So every batch, we have a certain number. We want a batch to be 4, then 4 of that will be random at any time, but random but non-overlapping, so that we make sure we go through all the data points, finish one epoch, and then loop back up. So in update T, update, wait, yes. So I will be introducing this idea of an optimizer. What is an optimizer? Last time you asked us, okay, yes, we know the forward pass, the backward propagation, but how do we actually update it? Because there are so many of them. So how do we do it? In PyTorch, we are introduced to this idea of an optimizer. So the optimizer will handle the updating of the model for us. So an optimizer just means that, recall, our objective is to reduce, to update the weights so that we can reduce the cost. And the visualization that we gave out all of the time is this ring. So this ring is like your height, like latitude, like altitude rings. And we want to go down the valley. So that is the idea. Like we want to go down, traverse down the valley of the weight landscape, but there are many ways we can go down. Last time we shared about the gradient descent, but vanilla, what is the vanilla gradient descent? The vanilla gradient descent is this delta invert is called nabla. Nabla is like you're calculating the gradient. J is, yes, synonym again. J, L, C, standing for cost or loss, or J is like an objective. Same thing. We want to minimize the cost. So this equation over here is saying that theta is the weight. We want to update the weight by going against the gradient using a certain learning rate, right? So this is the vanilla version. Oh, you calculate the gradient, then you times the coefficient, then you go against it. So that is the idea of gradient descent. Stochastic gradient descent just mean that yeah, you pick one data point at a time, right? One data point update, one data point update. So those are the two extremes that I just shared. There is stochastic gradient descent, individual data point. Batch gradient descent is take everything. So therefore, some people call the middle ground is the mini batch, right? But again, you can see how it can be confusing. Okay, is it a batch or a mini batch? If you understand the intention of the author, you will know what they mean, right? So yes, updating a batch instead of individual data points or the whole data set. And the big N denotes the number of data points in that one mini batch. So up here, you can see the cost function. Yeah, the cost function. So you also average them out across the batch n. So those are the vanilla gradient descent, right? But there are other idea of using momentum. So let's say you're a person on a hill and then you're running down, like you have inertia right now. Now it's physics. Now it's physics. So you have a certain inertia. So you are turning left, then you are keep going left. So now if I ask you to turn right immediately, then that will be quite hard. So it is the same idea of this optimizer. So it's not just about going down the gradient, but it also incorporates a certain variables called momentum. Do we need to go that deep into this idea? Probably not. No. So, but I just want to introduce this optimizer called Adam because it converts faster. So some people will just use SGD, stand for stochastic gradient descent, not Singapore dollar, and Adam is like the adaptive moment. So these two optimizer, and there's also this one idea of a learning rate scheduler as well. So the idea of learning rate scheduler comes from the idea that similar. So when you go down the hill, you know that you are very close to the bottom already. So you might want to take smaller step instead of big step, because if you take big step, you might overshoot. So the idea is after we have been learning for a while, we want to take smaller and smaller steps. So how do we understand this in a code, right? So now it's a coding time, right? No more dry lesson. Let's start with the code. So the code that I have shared earlier, yeah, if you follow the QR code, you land into this page. So first we import the various necessary libraries, but you can see that in the libraries there are like sub directory, subfolders. So the torch is the main PyTorch library, but then down here in .nn is where you you have the components, you have the various components to build the neural network, neural net. So that is why they call NN very informative. Here import torch function as F. So function, how is function different from layer? To be fair, technically, if you look through the NN and the functional, you can see that sometimes they implement the same thing 2 times. One as a layer and another time as a function, but they are effectively the same. If you apply a function at the end of a layer, it is as if the next layer contains that function. So, but then sometimes they just split it out like this for various reasons. And yeah, torch optim is where you find your optimizer. This is where you'll find your optimizer, various optimizer. Okay, up here is a dropout. Dropout I will be covering later on. But now I will be running through the model first, the model definition. So the model definition is first, yeah, call it the name. Name, what is the name? And then you initialize it. Initialize. Over here in the init, in the initialize function, you can put whatever you want. It is a class. It can store any kind of things that you want it to have. So for example, I can have like learning rate, self-learning rate. Yeah, you can put it here. It is just a storage of, it's a place to store variable, learning rate. Right. Equals LR. So I want to put in the different learning rate at different times. So probably I can also put an LR up here. So in the initializing, you can think of it as just, a storage space of variables. You don't really do anything here. And down here in the forward function is where you define how do you want the signal to propagate, right? So I think this convention is similar to you. Is familiar to you. On the left is the assign, like something being assigned. On the right is the function that is being assigned to it. And you read like from right to left. So over here, X is this X, so this is the input, right? So you go from right to left. So this X go into the layer number 1, and then it goes through the value layer and be assigned to X again. Then the X will be piped into the layer number 2 down here and reassign. Then we return the X. So this is the idea. So this layer 1 and layer 2 are defined up here. So you can see that linear, right? Linear layer also follows the same class structure, right? Class structure. So first you have to initialize the class. Then you can calling the class again, right? So model equals model bracket. This is initialize. And then if you do model X, this is calling the model, calling the object model. And when you put X over here, it will go through the forward function, right? If you put X in the bracket of a neural network, it will call the forward function. This forward is not forward, is a convention, right? Convention defined by the library class. You cannot change this. You cannot change. You cannot define forward prop. No, you cannot. It will become a different function that you can call it in a different time. So for example, if you do forward prop, right, self maybe X, then return X, then you cannot use model bracket open bracket X. You have to do the usual thing, model forward prop X. Yeah, you have to call the function again. But inside the library, they have identified that, okay, this forward will be mapped onto the calling of the model itself. Yeah, so that is the idea. So now, okay, so now you have a model. Let's explore what is in the model. Let's say someone handed down to you a certain model. Let's explore what is inside. So what inside is, first we initialize, then we do this parameters, no bracket. So no bracket just mean, let's say it is a variable. Then we inspect what is in that parameters, then it will share with us, okay, in your model, you have a layer number 1, which is a linear with input 1 to 8, output 1 to 8. It's biased. Yeah. So it print out to you all of the layers that you have defined up here. So when you type this out, it gives you a quick quick inspection. And if it is a bracket, then it is like a different object, different object. So it will come out as a generator. So I will not go down this idea of a generator in Python, but the idea is that it is a more compact way, right, to look through the various parameters in the model. So instead of storing them in like a list that you can iterate through, that can be very time consuming and storage inefficient. So the library has used this a generator object. So where is it used? So now we come to the optimizer. So this is where we start defining the optimizer even before we train. Before we train, we define our optimizer in order to, we define our optimizer. So to reiterate, the optimizer will handle the weight update for us automatically. Therefore, we have to put in, you can see here, model.parameters here. Parameter meters goes here. And you can see that when I type parameters, there is a bracket because it is a generator object. So this is a special data structure that Python use in order to like speed up or like store the various data more efficiently for calculation. Yeah. So yeah, there are two ways, the two optimizer that you can choose. Yeah, SGD or Adam optimizer. Getting from the optim, the optim import that we put up here. Yes, it is from the optim. So you can see that even though it is in the PyTorch library, they also package neatly like different aspects of the library for you to use. And after a while, you know where they are, right? So LR is your learning rate. So there is a default value, or you can choose it yourself. To know what default value they have, you can, yeah, you can open one of the links that we embedded for you. Yeah, Optim. Oh no, the quiz. Here, right? So Torch Optim. So now you can like try to read through and see, yeah, how to construct the optimizer. What are the various parameters that we can use, and what is taking an optimizing step means. It also provides you an example like this, right? So for input and the target, you see, it comes up again. Target now is the label. For input and label in the data set, 0 grad, output equals model input. So you put into the model feed forward pass, you get the output, get your loss function, loss backward, optimizer step. So yeah, so this the whole sequence is very important. So loss backward, what does loss backward do? Loss backward will calculate the gradient. The loss backward will calculate the gradient that is stored inside of that is stored in the model. If you recall, PyTorch operate on a data structure called tensor. So what does a weight mean? A weight is just a tensor. And what does the tensor in PyTorch hold? It is not only acting as an array to hold value. There is also another attribute that is called gradient to store the gradient. So when you trigger the loss dot backward, then the gradient will start updating. The gradient will be calculated. The gradient will be calculated. And so when the gradient is calculated, they are stored in the parameter. They are stored in this parameter bracket. Yeah, they are stored in the parameter bracket. And when we do the optimizer step just means, you know, update the parameters. So now the optimizer already have the information of what parameters I have, what parameters I'm in control of, in order to update it accordingly. Yeah, so model parameters go here. So this LR is the learning rate. It is the eta, the n-like symbol. Yeah, the n-like symbol. Weight decay. Okay, weight decay later on I will be sharing. So this idea of scheduler, right? So scheduler optimizer RL / underscore scheduler step learning rate. Yeah, so what it does is it will decrease the learning rate over time. So we put in the Adam optimizer. So now we do not just put in the parameters, we also put in the optimizer itself, because the optimizer is holding the learning rate variables here. So this learning rate is not accessible to the parameters, but the learning rate is an attribute of the optimizer. Therefore, if we want to change the learning rate, we have to put in the Adam optimizer inside the learning rate scheduler. And what does it mean? Step size. So after we call this dot step function 30 times, it will multiply the learning rate with a gamma. After calling 30 times, multiply LR with gamma. Right, so it will decrease. So where do you start stepping the scheduler? You start stepping the scheduler after an epoch. So as you can see in here, there is a loop, a small loop. There's nothing here, but assuming that there's training and validation goes here. So at every epoch, you do what just now the thing said. You read data, you get input, you get your label, then you get your output, prediction equals your model input, then you have your loss equals your loss function. So these are like placeholder. Like I have not defined them all. I have not defined them, but compare loss function between the output and the label, right? So after you have the loss, so first you have to add optimizer zero grad. So why does the zero grad very important? I will elaborate later. Now, actually, backward. So when you do loss dot backward, the gradient is updated. The gradient is updated in those tensor, in the neural network tensor, right? So what we want to do is we want to reset the gradient to 0. So when we calculate the gradient, the correct value of gradient show up, right? So after we revert the gradient to 0, then for example the gradient is like +2. Then when we call loss backward, the gradient is now +2. If we don't do zero grad, anytime we do the loss backward, it will just keep +2, +2, +2. So effectively, the gradient inside the tensor will become like +2, +4, +6, and those are not the correct gradient. Those are like artificially gradient created because you forgot to zero it out, right? So you zero, you calculate the gradient, then you step the optimizer, you update, then you step the scheduler, so that when it hit 30 times, learning rate decreases. Yeah. Then no, this is a dummy code. This is just a dummy code. I'm just loop through it so that you have a hang of what is happening. Because I think at this stage we only have like 3 workshops, so there are certain things that we cannot convey very clearly in such a short amount of time. So I just want to share with you the essence, right? The essence. So that is the optimizer. That is the one funny, not funny, but one short notebook to share with you, like how to initialize things and how to use them. Okay, so now we go to the bias and variance. Bias and variance, you might have heard this idea in your statistics and probability classes, and they also come back in machine learning and deep learning as well, because at the end of the day, they are probabilistic model. They are probabilistic model, meaning that they need data, and it is as good as the data they are fed in, and the thing that they learn is based entirely on data. So now that will dispel a lot of hype around AI and machine learning. But don't think that because they just learn from the data and you mock them, because the more data you have, the more it can cover it can do the things that you might not have predicted. Like ChatGPT, like no one thought that it can talk like a human, like it can give human speech or human syntax, but then it is trained on like billions of Wikipedia and Reddit, online. So it's probably quite good, right? The more data you have, the better it gets. So the idea of bias and variance. So if what I shared, if what we have been sharing about the training process, right? We want to decrease the loss function. We want to decrease the loss, the cost, and the cost is the similarity between the prediction and the label. And if the cost keeps decreasing, wouldn't it make sense to just let it decrease over time so that the label matches the prediction? Can we just let them run forever and then get a very small loss? So in response to that, no, we will run into a problem. The problem is called overfitting. So overfitting, as you can see on the left illustration, it looks like this. Yeah, it looks, so you are asked to separate the X from the O. So the best way, an appropriate way, is to like take a curve shape, like the middle. But when you overfit, you want to minimize any error. So the middle illustration have 2 errors, like the 2 crosses are in the wrong region. And if you keep reducing the losses over time, right, it doesn't want that. It wants to encapsulate all those crosses as well, and it will become this finger-like structure, right, protruding out. But we technically in the real life, we probably don't want this. we can live with some false positive, or false positive, but this is too much, right? This will not work very well. So that run the risk of overfitting. So what does overfit mean? Overfit is high bias. High bias. The bias is like, so let's say in this case, right, it is biased towards the 2x dot in the inside, right? In the middle, it takes into account all the x's and o's, but on the right, overfitting, it starts to the 2x's in the middle of the o's have more, have more leverage, right? Like they have to cover that part, so it bias. There's a lot of bias. So how about variance? Variance refers to the idea that, okay, there might be some error occurring, there it might not be as clear cut as you want, so that will be in the middle. So high bias can be followed by the low training loss and high validation loss. What does it mean? Because when you are overfitting on the training data, whatever is in the training data will be predicted very well, but what the thing that it has not seen before will score very low. So it is biased towards the training data, right? So when it sees a validation it has not seen before, it is using the knowledge that has been trained on the training data to detect the validation. So the moment you can see that the moment the validation loss goes up, probably it is overfitting. So that's why we introduced the idea of validation test set to prevent this thing from happening, right? To stop training around this time. So even though the error is still not the minimum, we know that it's time to stop, because it is because the more we train, the more it will overfit. So now we will introduce to the idea of a dropout neural net. So similar to we keep going back to the idea of bias and variance because they are intertwined with the idea of overfitting and underfitting. So in the standard neural net, all the connections are made, right? All the connections over here are made, and it is very dense. What drops out mean is that at some point in time, it will cut the connection. It will make this value become 0. So what does that do? So if we recall, if we use the same idea of a bias and variance, sometimes our neural net might favor a certain node, right? A certain layers, a certain node in the layer. So if we suddenly cut off that connection, will it manage to still perform very well? So it is not as biased towards that node anymore. So it has to figure out other ways to get to the bottom of the loss function landscape. Yeah. So it applied dropout. So it's just randomly turn on and off. And this turning on and off only happens in the training data. When you start inferencing, when you want to predict, then definitely all of them will be turned on. They will not be turned off. Because that will make the prediction goes very badly. So if we go back, we will have our dropout. Okay, dropout, right? So yeah, we initialize a layer of dropout, and then we input in a tensor. Just give it like 1, 2, and 3, right? And the probability of dropping out, probability equals 0.9. Yeah. So 9 out of 10 times it will be 0. Then we put the input through this layer to get the output. So the input is 1, 2, 3. So if the layer is an identity matrix, is an identity function, it should give us back 1, 2, and 3. But now you can see that is 0, 0, and 30. So 0, 0, you understand, okay, because it's dropping out, it is zeroing everything. But what about 30? So 30 is just an artifact of the idea of scaling, right? Of scaling the input proportional to the p value. Because right, so if we so why do we scale that? We scale it that way to make the model stable, right? Because now instead of having three active layer, three active, like let's say features, instead of having three active features, the other two is like missing. So the how do I interpret this in a understandable way? Yeah, you're losing something, so you have to compensate. So that is the idea. So you scale according to the probability. So probably, so if I change it into 5, so now what is the multiple value? So the multiple value is now is times 2. Yeah. So the idea is just to compensate, right? So now you see, just now it was 2, 4, and 6. Now it's 0, 0, 0. So the idea is, if now everything is 0, then I have nothing. So earlier I have to like compensate. I guess that is the idea. Yeah. But the point is that the dropout will force the neural network to update in a way that other layers will participate in the in the prediction better, not just some very specific one. So batch normalization, yeah, similar idea of normalization to like zero, center 0 with variance 1, like your Gaussian distribution probably. But batch normalization, you can see that, let's say if this is an image, right? So you have your height, your width, and then your other stack of images. So you want to get them all, like get the whole batch instead of just on one data point. Yeah. And this normalization, in order to get it to stabilize, it should be used in between the layer as well. Because if you normalize at the start, and then if you recall, we go through the linear layer with your linear regression, because a linear regression can also like, you know, explode in values. And then you do the ReLU just cut off the negative part, but it leaves the it leaves the positive part untouched. So yeah, the positive part can just explode into some big range. Therefore, batch normalization should be used in the middle of the various layer as well. So that is to speed up the conversions. And I think the last idea is regularization. Regularization refers to the idea that we don't want our model to overfit, and there is a potential for the model to overfit. And if it overfits, the weight will have a certain value, right? So if there is no regularization, the loss will be equals error, like y and y hat is the prediction and the label. So if there's no regularization, we have the standard loss function, and as we update, the weight will converge towards an overfitted weight, right? And we don't want that. We don't want that particular value of the weight. So now we nudge it somewhere else. Like we don't want to go there. So we add another terms in the loss function, which is like lambda and the sum of all the weight. So there are two ways. One is to use absolute, and the other one is to use the square. The idea is to make it positive, right? The idea is just to make it positive, because the idea is that, yeah, we want to punish the weight. We want to nudge the weight away. So if the weight is negative, then it will arbitrarily saying that, okay, this weight is good because this weight decrease our loss, and we don't want that interference. Therefore, this part is positive, this part is positive. And yeah, so what we are doing is like artificially inflating our loss function. So what happens if we do that? If we artificially inflate our loss function, then when we train, it will not converge to the overfitted weight anymore. So now when it converts to a different value of the weight that is not overfit, right? But the moment it overfits, or like it overly emphasizing a certain weight, then we punish it again. Like, oh, if the weight is like 10, then you have 10 plus the loss. So the loss now increased by 10. Okay, of course, there's a lambda term as well. 10 times lambda. So yeah, it is a battle. It is a battle between the various terms. So that is one way we can do regularization. And how does the regularization implement it? The regularization is implemented in here. Yes, weight decay. So it is under the optimizer, right? Even though we define it in the loss function, so it seems like it should be outside of the optimizer because the optimizer only update the weight. But because we define it in the loss function, and what happens when we want to update the weight? We have to take the derivative. We have to take the gradient. So as we take the gradient of the loss function, this lambda, this constant, you know, like if you do differentiation, then this constant will keep getting carried forward, and then it falls under the domain of the optimizer, right? So yeah, they put the weight decay here in the optimizer. So this 0.1 is this lambda here, and this particular weight decay is for the L2 regularization. No, not the absolute. Why is that so? I guess, yeah, it's always a battle between the absolute and the square. Like we want them to be positive, but do we want a smooth, you know, parabolic, not parabolic, yeah, parabola. Yeah, do we want a parabola or do we want like an absolute? But then I think a lot of people choose the L2, the square. So that's why it is implemented in the Adam in the optimizer, both any optimizer actually, any optimizer. So you can define it up here as well. So weight decay, you define it up here to prevent the overfitting. And okay, even though I didn't put it in the, didn't put it in the slide, but I think I can improvise the slide on the spot. So the idea is, at the end of the day, you have one big loss function. Let's say total loss. But inside the total loss, you can have different terms. So here you can have your, let's say your cross entropy loss. Then you can have your like regularization loss. Then you can have some other terms that you want to include. It is like the battle of the various factor. Okay, I'm going on tangent. There will be a break soon. I'm sorry, there will be a break soon. Let's use this idea. Yes. What does it do? So this structure of the neural network is just trying to, you have an input, then you push it to the neural network, and you have to replicate the input the same. Like you have to replicate the same input. So what do they want to do is they just want to get the, in the case of image, right? In the case of image, you have a lot of things happening in the image, but you want this image to go through a bottleneck to squeeze it down to a Z vector, which is smaller. But you also want to recover the image at the other side using only this Z vector. It is like a compression. Like you can compress all of the image, like height and width and channel, into this like Z vector, and then you can unroll the Z vector to get you the same input, the same output. So you can see like what are they trying to use? They are trying to use the reconstruction loss and the similarity loss. So so those are the two terms that will interact with each other to get you the reconstructed input, to reconstructed image. So what is reconstruction loss? Yeah, so they are comparing pixel by pixel. Is the output pixel the same as the input pixel? If not, then you are punished very hard, right? And then they will also similarity loss is in the middle, right? So it's something happening in the middle that they also want to punish. Yeah. So the idea is the total loss can have various terms, and when you define those various loss function terms, they should be meaningful, right? They should help the model learn the task that you want to do, and yeah, and let all the term battle it out, like as the loss decreases. So that is one interesting idea, is that there is no fixed loss. You can power on as many components. Okay, not as many. You can have many components depending on your use case. Yeah. So that is the first half. Thank you for following through. Now we can take like a 5-minute break. before we go to the second half. Thank you very much. Yes. So there was a question on what's the difference and what optimizer would you use? So I think it is very quite dependent on the task, or it is an exploration, right? People, companies have machine learning engineers to decide on these, which one is the best one to use. So the idea is the optimizer is just a facilitator. What we want is the model and the weights and at a particular value that will help accomplish various tasks. So at the end of the day, what we want to take out is the model and the weight, not the optimizer. The optimizer is only the part of the training. So what that means is that technically, yes, you can train like a few times using stochastic. You can train a few times with Adam. Yeah. So right. So my point is that it is not integral to the model. It is a part of the training process, and which one to use. So from the research, it is shown, or like it is demonstrated that stochastic gradient descent will be slower, but it tends to find the local minimum. So it tends to find the best place where the weight should be to get you the accuracy or to do the task that you want. But the Adam, right, because it has the momentum component, it can converge faster. So it really depends on, let's say, your needs and your requirements at the moment, right? If if you have a lot of time to spend and explore, then you can try stochastic gradient to see the very optimum, but it will be very slow. But if you want to push some product very quickly, then probably Adam. Yeah, so convergence and stability and higher chance of getting the local minimum. But that also depends on the complexity of the model and the architecture as well. It's just that, yeah, based on empirical data, generally the gradient descent, the basic vanilla type, get the local minimum done quite well. Yes. So now I will share my time to Aditya, another member of the academics MLDA.
Okay. Can you hear me? Okay. So good evening, guys. I'll be taking over the workshop now after Hui. No way. Okay. So now let's delve into the popular neural network architecture over the several years. So scientists have, computer engineers have always wanted to make machines learn on their own. They instead of giving fixed commands, they wanted the machine to be adaptable and to learn based on the provided data. So the concept of machine learning emerged in 1943, but due to limited computational power during that time, there was a void left in this research area. So scientists couldn't really progress much in this aspect. In 1956 was the turning point in the field of artificial intelligence when the term artificial intelligence was officially used in the conference. So this is when the whole the craze about AI started emerging, and then several research started popping up in this aspect. So in 1958, the term perceptron was used, which is still used in neural networks. Each neuron is referred to as a perceptron. And over the years, several algorithms and new methods have been developed, like LSTM, GAN, and UNet. And the more familiar ChatGPT is the most recent one, and it's commonly used in natural language processing. So as we can see, research in this field has grown tremendously. And this is grown hand to hand because of a large increase in the computational power. So yeah. This is the commonly used linear neural networks that I was told that you used in your last workshop as well. So this is like the basic architecture of any deep neural network or even shallow neural networks. So you pass in a bunch of inputs from the features, and it goes through the neuron. And after several training iterations, you get different weights, which are optimized by using several optimizers like gradient descent or stochastic gradient descent or ADAM and so on. And using that, you get the most optimal weights, and we perform matrix multiplications, and we will get the output. And the output is then passed through, added with a bias, and then passed through an activation function, which may include linear activation functions or ReLU, leaky ReLU, or in case of binary classification, sigmoid, or in case of multi-class classification, softmax, and so on. So that's how the basic structure in a systematic structure of a neural network works. But yeah, this is a very simple architecture. When it comes to image analysis and so on, we have more sophisticated architectures like convolutional neural networks, which we will look at now. So shall I play the, okay. So convolutional neural networks are popularly used for image analysis, mainly because of how efficiently it's able to detect the features like the geometry and so on. So how do I show it? Yeah. Oh, okay. So suppose this is the input image, and you can assume this, equate this input image to a matrix of about, okay, let's take 64 into 64. And basically how convolutional neural network works is that you pass in a kernel. So in this case, we pass this 3 by 3 matrix, which essentially convolves over the image. So the term convolve means that you take in this kernel, which is the 3x3 matrix, and you essentially just hop on, flow through the image. And during this process, you multiply this take the dot product of the values here, and you multiply it with the pixel images there. So in doing so, you will effectively be able to capture several of the features. So in this case, you can see the white lines captured here are efficiently captured here, and so on. So using different kernels, which you can refer to as filters as well, you can effectively capture vertical lines, horizontal lines, or as you pass through the convolution deep into the neural network layer, you will be able to capture faces or eyes, ears, nose, and so on. So this is effectively how convolutional neural network works. And it has proven to be much more efficient in terms of image recognition as compared to just using normal deep neural networks. Where's the PPT? Yeah. So as I said, you can use several kernels, and using those, you can detect simple features like horizontal, vertical edges, and so on. As you pass deep through the networks, you can detect more sophisticated features. So yeah, so as I said before, CNN weights are the values of the kernel pixels, which is the 3x3 matrix that we saw in the website. So when you initialize the convolutional layer, the filter is randomly initialized, and using several of these filters, you can detect several important features that's present in the image, which in turn is able to efficiently detect the image used in image recognition. So yeah, the weights in the kernel can be adjusted to make the detection better. So that's how you optimize the CNN model, and so on. Do I need to play this? Yeah. Yeah, so this is how the new CNN architecture looks like. So in a simple DNN, you just use layers like linear, ReLU, or sigmoid, and so on. And each of the outputs get passed to the next layer, and it propagates through the neural network. But in case of CNN, you introduce convolutional layers. So each of these layers are filled with different filters that are randomly initialized, and each of these filters leads to detection of specific features in the image. So as you can see in this image, you can detect the front, the hood of the car, and in this one, you are able to detect the front features and so on. So this is like the first layer, and as you pass through the convolutional layer, you'll be able to detect more complex features. You may have noticed the layer called pool. So this is essentially max pooling. So I'll get to this in the next slide, but essentially what it does is it helps to reduce the dimension, and it leads to it helps you to find the most dominant feature in the image that has been produced upon using convolution. So that's how you propagate through the CNN architecture, and then you can get the highest probability of the detection, which here is car. So yeah, just as we saw on that website, this is how convolution works. You can use different filters initialized with several values like -1, 0, and 1, which essentially just corresponds to -1 being black, 0 being gray, and 1 being white, and so on. And you can just go through the different pixels in the image, and you can produce the convolved image. And this is how it will look like. And as I mentioned before, yeah, this is what max pooling essentially does. So suppose you set a max pooling filter of as a 2x2 matrix. You essentially just assume that this is the image that's produced upon performing convolution. And as you go through the image, you need to select the value that's the most dominant. So in this case, it's 6. In this case, it's 8. Here it's 3. Here it's 4, and so on. So essentially, what it does is that it's able to detect the value that's the most dominant, and you are just like discarding everything else. So this heavily reduces the computational resources that's required, and at the same time, you can efficiently detect the features as well. So max pooling is just one of the many pooling features that are available in CNN. There's also average pooling, essentially just performing mean on the on this filtration layer, and then you will produce the max pooled output. So, but the most commonly used and the best performing method is max pooling, and that's what we will be using in our activity as well. So now let's proceed to the hands-on activity where we will be implementing CNN on the Cypher dataset.
So yeah, for the people who are here, you can follow the QR code. It's a different notebook altogether. When we share the notebook, we will combine them all. Anyone?
Okay, so I will be explaining along as we run the different cells. So essentially, we will be using a framework that has been used in the past workshops as well, which is PyTorch. And this is the deep learning Python library that we will be using in this workshop. There's also TensorFlow, but PyTorch has been becoming more popular nowadays, and it's better maintained by Meta. So we recommend that you use PyTorch. Yep. So the first few lines in is just you inputting importing different libraries that are essential for this activity, and then as we would have explained, we will be performing some data augmentation on the images that are present in the Cypher dataset. So before moving on, Cypher dataset is an open source image dataset that has about 10,000 plus images, if I'm not wrong, with several thousand classes of images. And this is quite widely used in image recognition as a beginner's guide to beginner's step to image recognition. So yeah, as I was saying before, this is the part where we perform data augmentation, where essentially we increase the variety of the training data set. So we take one image and we perform maybe a horizontal flip, or we can vertically flip it, or just crop a part of the image and input it, or we can introduce some random rotations, or maybe some noise, or even like altering the contrast, brightness, saturation, and so on. Essentially, this prevents overfitting, which we would have explained, and allows the model to perform more robustly when introduced to a newer image that's not present in the training dataset. So yeah, upon doing that, we will be performing normalization, which essentially just like warps the values between particular range. And in this case, 0.5 here is the mean, which we will be introducing into the 3 channels of the image, RGB, and this is the standard deviation, which is also 0.5. So essentially, we take different RGB values and we compress them between -1 and 1, such that the mean of the batch becomes 0.5 and the standard deviation also becomes 0.5. Upon doing that, we will be importing the importing the Cypher data set, and we will be storing the training data images into the train set augmented. And upon doing that, all the images involved in training will be stored in the train loader augmented. So essentially what that does is we will be choosing a batch size of 4, and then we'll be storing it in from train set augmented, and we'll be storing it in train loader augmented. Upon doing that, we will be performing some transformations on the test data. Wait, what is this? Why are there two? Yeah, this shouldn't be there, right? Actually, this needs to be there. It's for the test. Yep. So yeah, sorry about that. Here we will be performing some transformations on the test data as well. But in case of test data set, we don't need to perform augmentations because in real life scenarios as well, we want to recognize the actual image. We don't want to recognize a rotated image or a part of the image or so on. Data augmentation is something that we do on the training set alone, and it's only to increase the robustness of the model. So in case of test data, we will only be performing the normalization, which again just warps the values such that the mean essentially becomes 0.5, and the standard deviation for all the channels also becomes 0.5. And the same thing we'll be doing in this cell as well. Essentially just, okay, this step is a repetition as well. I will be removing this. In this case, we will be storing the test images into test loader. So this part is just for visualization purposes. So as you can see, the Cypher dataset has several different classes like planes, cars, birds, cats, and so on. And we will be just displaying random 4 images. So if you run the cell, it will randomly select 4 images and display. In my case, okay, I don't know what this is, but this looks like a deer. Oh, okay, this is a horse, plane, and this is a cat and cat. Yeah. So each of you will be getting your a random image that's present in the training set. Yep. Okay, so this is the part where we will be defining the architecture of our CNN. So this is defined under the class net, and essentially, as you can see here, we will be first introducing a convolutional layer, and upon that doing so, we will be introducing a pooling layer. So it follows hand in hand. So upon performing convolution, you immediately like input it into a max pooling layer, and this will just reduce the dimensions and highlight the features that are the most prominent in the image. And there are several other layers like linear and so on. And basically, it's just a different permutation combination that you perform, and maybe you can arrive at a different architecture, but this is what we will be using for this workshop. So essentially, in any deep learning based activity, you will need to spend quite a lot of time in defining the architecture, which will involve you performing like choosing some random values in the beginning and then optimizing it to suit your training set. So this is for the forward propagation. And first, we will be assigning a ReLU on the convolutional layer 1. And upon doing that, we will be assigning a ReLU activation function on the convolutional layer 2 as well. Upon doing that, finally, we will be flattening out all the dimensions. So initially, you might have noticed that the values are in the form of a matrix. But in this case, we will be flattening it out such that it's a one-dimensional NumPy array now. Okay, it's not necessarily NumPy array, but yeah, it's an array, a one-dimensional array. And finally, we will be passing that into a ReLU, and following that, we will be using another ReLU. And finally, we will be getting multi-class classification, which could range from 0 to several thousand, depending on how the classes are labeled. So yeah, this is the part where we will be performing the training. So we will be using cross entropy loss, which is commonly used. Okay, it's just commonly used for multi-class classification. In TensorFlow, it's called sparse cross entropy, for those who are into TensorFlow. So that's the loss function that we'll be using for this architecture. And for optimizer, we will be using stochastic gradient descent. Atom also works, but as Hui said, stochastic gradient descent is much more robust when it comes to finding the minimum, mainly because SGD introduces a bit of noise in every iteration. So even if every iteration is a bit inaccurate compared to gradient descent, it ultimately leads to a better performance. And there is a whole lot of research being done on why SGD is better than gradient descent, but it's just maybe you can look into it if you're interested. But yeah, we will be using SGD for this architecture. So we will be performing 2 epochs for this training. So as we would have explained earlier, epochs is just how many times the model looks at the data set. So in this case, we will be doing it 2 times. And yeah, so essentially that's how it trains. So initially, we will be assigning a training loss of 0 initially. And then for each of the example in the training set, we will be storing it into inputs and labels. So labels is the final class output, and inputs is there several features that are present in the image. So we will be assigning 0 gradient parameters to the optimizer initially. And yeah, and then in this part of the code, we will be performing forward propagation, and then upon calculating the losses, we will be back propagating and then adjusting the weights, and this carries on several iterations, and then we will be optimizing it and finally getting the weights that are the most optimal. So yeah, finally upon running this cell, you will be getting a loss for each of the set of images that are first on which the training is performed. So after seeing the first 2000 training images, you can see the loss is about 2.243. But after seeing the next 2000, you can see the loss is reducing to 1.95. And this continues until 12,000 images, which is like the end of the training set. You can see the loss reduces to 1.625. So that marks the end of epoch 1. And then we will be stepping into epoch 2, which is a time when the model looks at the image one more time. And it continues to reduce. And yeah, we stand at a final loss of about 1.482. Again, it might be different for each of you. So yeah, but it will be comparable. And you can use more epochs if needed. But then again, more epochs might lead to overfitting. So it's a whole other technique again. So more if you're using more epochs, then you'll need to use more better regularizations. And in case of underfitting, you will need to use more epochs, but in case of overfitting, you will need to use regularization. And yeah, there are several factors that defines how well the model works. So it's not like set in stone as to how many epochs you need to use. It depends on what you are encountering when you're training. So yeah, now let's we are basically storing the network's state in the cipher net.pth. So this is basically the weights file, and what this does is that this stores the weights that have been found upon producing the performing the training, and you can store this weights. So essentially what this does is that you don't need to train the model again in the next time you're using this model. So you can just import the cipher net.pth, and you can immediately start predicting using that. So this saves a lot of time, and this is essentially how researchers exchange their the weights that they have produced upon performing deep learning operations. So now let's iterate through the test data, and this is some images that are present in the test data set. So this is also the ground truth which we will be using to predict. So yeah, I got a cat, ship, and plane. You might be getting something else. So yeah, it's just completely random. Now this is the part of the code where we'll be inputting these 4 images into the model. Actually, this is the ground truth, but when we put the features in the neural network, this is the prediction that we get from the network. So we get cat, ship, and instead of plane, it's detected as ship. So we can see that it does make mistake, but it got 3 out of 4 of the images correctly. So yeah, you can improve the model in the future by using a different architecture, by using different layers like ReLU in between, or you can introduce more max pooling layers or more denser convolutional layers, and so on. So there are several ways to improve the model. And yeah, so that pretty much sums up the CNN architecture. What is this one? What are these two?
I think the bottom one is not run. This one should break down the various accuracy of the 10,000 test images, and also like break down the various classes. So as you can see, there are CIFAR 10. So if you go to the website, there are like 10 classes, and the bottom two will break down like the percentage, right? Accuracy for individual class. But I think at this stage, it doesn't run. I think we forgot to run it. So you can take a look and see how it turned out. So, and then during yeah, I think we already commented here, but you can see that with torch, no grad. So the idea is we are in the inference phase, so the gradient is no longer necessary. Yeah, so we put it just to prevent the gradient from accumulating. And yeah, that should be it. So over here, you can see that the code required to probe and inspect the data is more than the training code, if you look at that. So so I think what we have been sharing is the core idea, the core workflow. But in order to help visualize and demonstrate, so you as an engineer also need to demonstrate your work with other. So that is where all the images or the breaking down of the classes, the accuracy also helps in your demonstration. Yes. So therefore, you can take a look, and in this, you can see that the code employs various Python syntax. So over here, this is called the dictionary comprehension, like comprehension. So the idea is you don't go down and comprehension. You don't go and add various data point to the dictionary or list, but you loop it in a certain way. Yeah. And then there's also this zip function. The idea is that we will, so the label and the prediction, let's say they are a different list, right? List number 1, list number 2. When we zip them up and we break them down, so in Python syntax, for something, in something. So in something is we are iterating through an iterable, something that has a bunch of values that we can ask at individual index. So this zip will combine them together. So let's say at location 1, you have label and prediction, then it will return the label and prediction accordingly, right? So this is a very useful way to like entangle two arrays. Yeah. So yeah, we want the correct the prediction with the corresponding label. Yeah. So that this is a zip, a function, a technique in Python. It is very useful. So as you look through, you can take a look of the various implementation of Python.
So yeah, I hope you guys would have run the code and would have gotten something similar, the results that we've gotten. Maybe your model would have predicted all 4 of them correctly. So if so, then good job. So yeah, that pretty much wraps up our hands-on activity which involves, oh yeah.
So participant ask us this code block. We are not training, so we don't need to calculate gradient. Yes, so your question is this, right? So technically, right? Technically, we don't need this. And because we do not have the loss dot backwards, it will also not updating any gradient. But it's just that with this, it is more explicit, right? It is more explicit that there shouldn't be gradient propagate, because what we're doing here is just inferencing. Calculate output to this is inference. Yeah, it's not training, it's inference. Inference. Right, because you see we are operating on a test set, and in the test set we take out the image and the label, and then at the end we just compare if the label is correct or not. So we are not updating. Yeah. So if you, so the thing maybe some thing that we can try is A equals torch tensor 1 2. Let's see what we have. Print A. Oh, it's oh, okay. Oh, right. Just start. Torch. Print A. Ooh, yeah, it needs to load in the torch. Oh, tensor. Oh, require. Oh. None. Yes, so you can see that in a torch, we can query this value called grad. Yeah, so implicit in the tensor torch tensor is a gradient. So at the moment it is none. So let's see, right? Let's see. So we have C equals 2 times A. C backwards. Oh, and then we print A grad. Is it correct? Element 0 does not require grad and doesn't have grad function. Who require grad true doesn't have a grad function. Element 0 of tensors. Okay, maybe we try a different thing. Torch random. 2 1. Does it have gradient? Backwards. Okay, it does not require gradient. So yes, so you see, so this is an interesting observation, right? The idea is that each of the tensor will have an associated gradient, and as you add on the various operation, it will start defining a gradient function. But over here, there are some syntax error, some rules that we have to follow, but at the moment we are not following them. So there might be some problem at the back end, right? From some problem from our syntax side. But my point is that in the whole training workflow, yes, the gradient, the A dot grad is constantly being recorded and updated. Yeah, in this case, when we query it is none. So it's the same idea for the torch dot no grad. So when we do torch dot no grad, then it just turn off the gradient. It doesn't accumulate anymore. So I assume that it can like speed up the calculation because it doesn't need to, look into the gradient as it calculates things. Yeah. So I think that is all for the code, and now I think is a Q&A session. If you have any question, do raise your question. Yes. Yes, so the slide will be sent out and will be up. May I ask, how do you know about the workshop? Are you a triple E student? CS? I mean, oh, okay, okay, it's okay. Yeah, thank you. So are you aware of our handbook? About handbook? I see. So yeah, so just an introduction, a quick introduction for everyone who might not know. So the whole series of workshop is actually, yeah, we built up from beginner all the way to like advanced level, all the way into semester 2. And at the start of the year, we did advertise it, and many of you have registered. So what we're trying to do is to build up the competency. It's like a night class parallel to your schoolwork, but at a slow pace, but focusing on the practicality. Yes. So so you follow the Instagram, but do you know about the Telegram chat? You also don't know about the Telegram chat. Yes. So I think we will be sharing this handbook. This handbook is public, so you can also share with your friend as well. Over here, when you scroll down, you can see all the previous workshop that we have been through. Yeah, and including the recordings and the collab. Yeah. And I hope you also follow us through in the future as well. Yeah, those are the collab will be updated. Will be updated. I believe that you have my email. We send out the email notification. So maybe drop us an email if you want the handbook link. Yes. Oh, so I think at the end, I hope you can follow, give us a feedback and also try out the quiz for today's session. Yes. Yeah. I ran the code. I'm wondering how to improve the accuracy of the model. Changing layers manually, anything like grid search, CV search, random search. Okay. Yes. So yes, one of the member in the audience raised this point of the idea of search. So today we have shared about the idea of hyperparameters with the same architecture, with the same values, with the same same architecture. There are still many things that we can tune and tweak. And what do we do to like search them through? One thing we can do it manually, or like like what the person suggested is grid search. Basically, you yes, you perform different permutation. Like let's say put a minimum, a maximum value, and then make a grid, right? Like chop down the various interval.
Like try different learning rates.
Yes. So that is where your GPUs come in, right? Because you need to run it and like log out the values many times. So that can be time consuming. High tuna hyperparameter optimization. Optuna. Okay, yes. So there's a Python framework called Optuna that you might want to look into specifically to answer the question of the member. So yes, it supports various machine learning workflow. So the idea is when you have the Optuna, you only need to add in a few more layers of code, and you set the end, the start, and then it will automatically like run through the iteration and find out the best hyperparameter. Yes. So it's not just grid search. I think the way they implemented it is like adaptive search as well. So after a while, it pick random points, and yeah, similar to gradient descent, it will see which points will give better performance, right? So it will search at that nearer to the point with good score. So that you can say it as fingers. There's an algorithm at the back to adaptively search. So yes. Yes. So instead of like you manually doing it, there's a library for that. So that is one thing that I can suggest. Yeah, thank you. Thank you. And so the participant in our lab, have you followed the QR? Yeah, I hope you do as well. So even if you're not a part of the members, you can also try the quiz just to refresh your memory and yeah, make sure that everything is clear cut. So with that, I think that is all for today. Any final question from the online audience? Yeah, so to add on, the what we have shared today are like various expansion of the same concept. That is what the machine learning engineer do in real life, right? So it sounds very hype. There's a lot of hype recently, but then those hype might not translate to the immediate, job description. I think at the moment, various job description is still catching up. It's still playing catch up. But the knowledge, the state of the art is also being trickled down. But many times they still need fine tuning and make the general model work for their specific use case. Yes. So that will be all. I think I will be ending soon. Yeah. If you don't have any question, you can, feel free to leave. Thank you for coming.
Thank you very much.
And hope you continue to follow in the upcoming weeks as well. Okay.